Good morning, everyone. So, in this class, we will start with the partial differential equations in cylindrical and spherical coordinates. And whatever we have done in the last class, if you remember that we started the problem with the cylindrical polar coordinate. We considered a two-dimensional problem first, that was one dimensional in time and one dimensional in space. Now, we have seen that in cylindrical polar coordinate, which will be typically the flow occurring in a pipe or a tube, the coordinate system will be given by the radial polar coordinate system, and we have looked into the operator. The operator in this case is 1 by r del del r del del r. Now, we have seen that for this particular case, the eigenvalue problem becomes the Bessel equation. It is formed in the Bessel equation, and the solutions will be constituted by the Bessel functions, and we have already solved the problem that the eigenfunctions will be Bessel functions, and we have proved that the Bessel functions are orthogonal to each other, and using the orthogonal property one can completely solve the partial differential equations in cylindrical polar coordinate system. Now, in today's class, we will be looking into an example of cylindrical polar coordinate system, where the problem is more than two dimensional. It is two dimension in space and one dimension in time. So, therefore, it is a three dimensional problem. So, we call this problem as transient heat conduction in two dimension polar coordinate system. So, the governing equation in this problem becomes del u del t is equal to 1 over r del del r r del u del r plus 1 over r square del square u del theta square. So, if you look into this problem, the operator is del del t minus 1 over r del del r r del del r plus 1 over r square del square del theta square. So, that is the operator we are talking about. So, therefore, this equation requires one initial condition with respect, because it is order 1 with respect to t, and two boundary conditions over r and two boundary conditions on theta. Now, let us set up this problem by fixing up the initial and the boundary condition. The initial condition is that at t is equal to 0, u may be a constant, or it may be a function of r, it may be a function of theta, it may be a function of in general r and theta. So, this may be the general initial condition, that u may be function of r and theta both, and or it may be constant, it may be function of r alone, may be function of theta alone. Now, let us set up the boundary conditions. If you look into the boundary conditions, that at r is equal to 1, we have u is equal to 0. This simply means we are maintaining a constant temperature at the wall. R is equal to 1 means it is in the non-dimensional version. It is in the dimensional form. This boundary condition is deciding at the surface, r is equal to capital R, and where we are having a temperature, let us say we are maintaining a constant temperature T is equal to T1 there. Now, if you define a non-dimensional temperature T minus T1 divided by T1, then this boundary that transformation or changing variable will be reflected in the form u is equal to 0. So, therefore, this means we are having a homogeneous boundary condition at the wall, and at r is equal to 0, as we have seen in the earlier class, that the value of u is finite or bounded. So, we do not know what is the value of temperature at the center of the whole tube. So, therefore, but it will we know that it is assuming a finite or bounded value. So, therefore, this is a physical boundary condition, as we have mentioned in the earlier class in theta. So, these are the boundary conditions on r, and on theta So, these are on r, and on theta we will be having again the periodic boundary conditions, that is at u at theta is equal to pi should be is equal to u at theta is equal to minus pi, and del u del theta at theta is equal to pi is equal to del u del theta at theta is equal to minus pi. So, these are called periodic boundary conditions. Again, these are the examples of physical boundary conditions. In addition to this is also physical boundary condition. Thus, we have a system where we will be having the physical boundary conditions which will be governed by the physics of the problem. So, with this set of initial and boundary conditions, we can go ahead with the solution. So, since the operator is a linear operator, we can assume that the solution will be constituted by three functions. Each of them will be independent, each of them will be a sole function of the independent variable. So, let us assume that u is constituted of product of three terms. One is r as a function of r, theta hat that is a function of theta only, and t that is a function of temperature, the function of time only. So, now we substitute these in the governing equation as we have done earlier and divide both sides by r, theta hat and t. Then what you get is that 1 over t dt dt is equal to 1 over r r d dr r dr dr plus 1 over r square d square theta hat d theta square. So, exactly like the earlier problem, we try to set up an eigenvalue problem. So, we make it 1 over t dt dt, okay, minus 1 over r r d dr of r dr dr. So, we bring it to the other side. So, this becomes 1 over r square d square theta hat d theta square. There will be a theta hat in the denominator. Now, we multiply both sides by r square. So, this becomes r square 1 over t dt dt minus 1 over r r d dr of r dr dr is equal to 1 over theta hat d square theta hat d theta square. Now, the left hand side is completely a function of t and r, the right hand side is entirely function of theta. Let us say, so they will be equal, and they are equal, and they will be equal to some constant, let us say mu. So, theta, so we select a value of mu, so that you will be getting a non-trivial solution. If you select mu is equal to 0, let us see what you get. You will be getting d square theta hat d theta square is equal to 0. So, therefore, the solution is theta hat is nothing but c 1 theta plus c 2. Now, if we use the boundary condition that theta hat at pi should be is equal to theta hat at minus pi, then what you will be getting is c 1 pi plus c 2 is equal to minus c 1 pi plus c 2, and c 2 will be cancelling out. So, pi is not equal to 0. So, what you will be getting is c 1 is equal to 0. So, that leads to the solution of theta. The theta is theta hat, the theta hat will be giving you c 2 a constant. Now, if you use the other boundary condition del u del theta del theta hat del theta d theta hat d theta at theta equal to pi, and d theta hat d theta at theta is equal to minus pi, what you will be getting is that you will be getting c 2 is equal to c 2, you will be getting an identity. So, therefore, the solution of theta hat for mu is equal to 0, this constant equal to 0 is theta hat is equal to C2, that means it is a constant. Now, let us consider mu is positive. Now, if mu is positive, you can go ahead with the solution, that means d square theta hat d theta square minus mu theta hat is equal to 0. So, it is positive. So, you will be and you utilize the boundary conditions that theta hat at pi is equal to theta hat at minus pi and d theta hat d theta at pi is equal to d theta hat d theta at minus pi. You will be landing up with a trivial solution. I am not going to do that. We have solved this type of equation number of times earlier classes. So, please do go ahead and solve this problem by yourself. So, you will find out that you will be getting theta hat as a trivial solution. So, it will be getting the solution is basically theta hat equal to 0. So, mu cannot be positive, the positive constant is ruled out. So, let us look into the negative constant. If theta hat is negative, is mu is negative. So, that is the other case. So, mu is negative. So, minus alpha. So, this value is negative. Okay. So, now what we will do? We write down the governing equation and of theta hat and see how the theta hat varies with theta this time. So, this becomes d square theta hat d theta square plus alpha square theta hat is equal to 0. So, the solution is constituted by sine function and cosine function. Therefore, theta hat as a function of theta is nothing but C3 cosine alpha theta plus C4 sine alpha theta. Therefore, if theta hat at pi and theta hat at minus pi, we use this boundary condition, we will be getting as C3 cosine alpha pi plus C4 sine alpha pi is equal to C3 cosine alpha pi minus C4 sine alpha pi. So, if you look into both sides of the equation, this cos term will be cancelling out. So, you will be getting C4 sine alpha pi is equal to 0, twice of that. So, in order to get a trivial solution, sine alpha pi, in order to get a non-trivial solution, sine alpha pi must be is equal to 0. For C4 not equal to 0. Now, let us use the other boundary condition, that is the d theta hat d theta is equal at pi and theta is equal to minus pi, and see what we get. If we use other boundary condition, theta hat prime evaluated at pi is equal to theta hat prime evaluated at minus pi. So, you will be getting minus 3 sine alpha pi plus C4 cosine alpha pi is equal to C3 sine alpha pi plus C4 cosine alpha pi, and C4 cosine alpha pi will be cancelled out from both the sides. You will be again getting sine alpha pi is equal to 0. So, from both the boundary conditions of on theta, you will be getting the same equation alpha pi. So, therefore, we know the for a non-trivial solution. So, we will be for C3 not equal to 0. Okay. So, in the other boundary conditions, we came to a conclusion sine alpha pi is equal to 0 for C4 is not equal to 0. In this case, we are getting sine alpha pi is equal to 0 for C3 is not equal to 0. For therefore, the eigenfunctions in this problem will be constituted by the both C3 is not equal to 0 and C4 is not equal to 0. So, therefore, combination of sine theta, sine alpha theta and cosine alpha theta both will be formulating the eigenfunction. Now, let us look into the solution of this general solution of this is nothing but, as we have already seen earlier, alpha pi is equal to n pi. So, therefore, alpha is nothing but n, where the index n runs from 1, 2, 3 up to infinity. So, let us write down the eigenfunction in this case, C 3 n cosine n theta plus C 4 n sin n theta. Now, if you put n is equal to 0, then what you will be getting is that for n is equal to 0, this term will vanish, because sin 0 is 0, but cos 0 is 1. Therefore, you will be getting C 3 n, that is a constant. And if you remember that for the value of mu equal to 0, we had a constant value of theta. So, therefore, if we write the index from 0, 1, 2, 3 up to infinity, that will include all the cases that mu is 0 and mu is negative. So, theta is constituted by cosine n theta and sin n theta is an eigenfunction for this particular problem, with the index n running from not 1 to 3, but from 0, 1 to 3 up to infinity. So, therefore, it includes the term for the situation where mu is equal to 0. Okay, we obtain the eigenfunction in the theta direction. Now, let us look into the eigenfunction in the r direction. If you look into the solution of the other part, r square 1 over t dt minus 1 over r d dr is equal to minus alpha square. So, therefore, minus alpha is, we have found out that alpha is equal to n. So, it will be minus n square. Okay. Now, n is from 0, 1, 2 up to infinity. So, what we will be getting is 1 over t dt minus 1 over r d dr of r dr is equal to minus n square divided by r square. So, we bring it on the other side. So, 1 by t dt is nothing but 1 over r d dr r dr minus n square r square. Now, the left hand side is entirely a function of time, the right hand side is entirely function of space in r. They are equal, therefore, they will be equal to some constant. Let us say this constant is a negative constant. We can prove that if this constant is 0 or positive, we will be getting a trivial solution. That means, for constant is equal to 0 and positive, we are going to get a trivial solution, but we are not looking for a trivial solution, we are looking for a non-trivial solution. Hence, we solve the r varying part d dr of r dr minus n square divided by r multiplied by r plus lambda square r is equal to 0. Now, let us set up the boundary conditions on r. The boundary conditions on r must be satisfying the boundary condition of the original problem in the small r direction or coordinate system. So, therefore, the boundary conditions will be at r is equal to 0, capital R is bounded, that means it is finite. At r is equal to 1, capital R is equal to 0. So, these two boundary conditions, if you remember, the original problem used to satisfy in the r direction. So, r varying part must satisfy these two conditions as well. Now, if you look into this equation, if you see the nature of this equation is nothing but the Bessel equation of order n. So, it will be constituted of the solution of this equation will be constituted of the functions nth order Bessel function j n r and y n r. So, therefore, let us write down the solution of r varying part. R varying part, the solution is C 1 j n lambda r plus C 2 y n lambda r. Now, we have two boundary conditions on r. we utilize them at r is equal to 0, your capital R is finite. So, if you remember the variation of y n as a function of r, y n is infinite at r is equal to 0. So, therefore, it increases from infinity and then it oscillates about the r axis with a diminishing magnitude. Therefore, to have a finite value of r at smaller equal to 0, the associated constant must be equal to 0. So, C 2 equal to 0, we have the solution as C 1 j n lambda r. Now, we utilize the other boundary condition, r is equal to 1, capital R is equal to 0. So, 0 is equal to C 1 j n lambda, where C 1 is not equal to 0. If C 1 is equal to 0, then we are going to get a trivial solution. So, therefore, the other option is j n lambda is equal to 0. Now, what is this lambda? Lambdas are basically the roots of this equation. Again, you have standard ready-made program in C or Fortran, where you can compute the roots of this equation or zeros of this equation to find out the eigenvalues. So, eigenvalues of this problem, we write it as j n lambda m n is equal to 0. So, eigenvalues are lambda m. So, m runs from 1 to infinity for every value of n. What is this n? These n are basically whatever we have found by solving the theta varying part. So, we write r m n is equal to C m n j n lambda m n times r. So, lambda, what is lambda m n then? Lambda m n is nothing but mth root or 0 of Bessel function of first kind of order n. So, that solves the problem. Then we get the expression of T m n. T m n, if you look into the time varying part, you can easily find out that its solution is some constant multiplied by exponential minus lambda m n square times t. So, we get the complete solution of u r theta t as summation 2 summation 1 is over n, and if you remember that n varies from 0 to infinity, it is not from 1 to infinity, n varies from 0 to infinity, m varies from 1 to infinity, exponential minus lambda m n square t j n lambda m n r multiplied by d m n sin n theta plus E m n sin cosine n theta, because the theta varying part contains both the terms C 1 and sin and cosine, and the associated constants are not equal to 0. So, therefore, you will be getting this solution as a general solution to this problem. Now, the only thing that is left is that one has to find out the constants d m n and E m n. We have the boundary condition or the initial condition at t is equal to 0 unutilized. So, we can utilize the initial condition. We use the initial condition at t is equal to 0, u is equal to u naught as a function of r theta. In general, it may be a constant, it may be a function, prescribed function of r, a prescribed function of theta, or it may be a prescribed function of r and theta. So, if you write it down, then u r theta becomes summation of n is equal to 0 to infinity, summation m is equal to 1 to infinity. You have d m n sin n theta plus E m n cosine n theta multiplied by j n lambda m n theta. lambda m n r. Okay. Now, what we use? We use the orthogonal property of sine functions, cosine function and Bessel function. We use the orthogonal, the eigenfunctions, sine functions and cosine functions are orthogonal to each other, as well as the Bessel functions are orthogonal to each other. We have already proved that earlier in the last class, that Bessel functions are orthogonal functions. So, use the orthogonal property. One can evaluate the constants dm and em. We have done these things lots of time earlier. So, I am not going to do it once again. So, I am just writing the final expression at r is equal to 0 to 1 integral theta is equal to minus pi to plus pi, that is the domain of variation of theta, r j n square lambda m n r cos square n theta dr d theta, that is the denominator. In the numerator we have r is equal to 0 to 1 and theta is equal to pi to minus pi, u 0 r theta r j n lambda m n r cosine n theta dr d theta. Okay. This is the value of E m n, because it is associated with cosine n theta. So, it will be cos square n theta. So, this is now the d m n, this is the expression of E m n. So, now let us write down the expression of d m n. The expression of d m n goes like this. Okay. 0 to r is equal to 0 to 1, theta is equal to minus pi to plus pi, r j n square lambda m n r sin square n theta dr d theta, r is equal to 0 to 1, theta is equal to plus pi to minus pi, u 0 r theta r j n lambda m n r, this will be sin n theta dr d theta. So, that is the expression of d m n and E m n one can get, and knowing the prescribed function of u 0 r theta, you can evaluate this integral analytically, or one can take recourse to the numerical techniques to evaluate this integral using trapezoidal rule or Simpson's 1/3 rule. Now, the point is, if we can do a slight simplification. If u 0 r theta is only u 0 r, that is, it is independent of theta, then you will be having d m n is equal to 0 for n is equal to 0, 1, 2 up to infinity, E m n is equal to 0 for n is equal to 1, 2, 3 up to infinity. So, the difference here is, here it is n starts from 1, 2, 3 and here n starts from 0, 1, 2, 3. So, E m 0 is not equal to 0. So, solution boils down to u r t is equal to summation m is equal to 1 to infinity E m 0 exponential minus lambda m n square t j 0 lambda m 0 r. So, that is the solution in this particular case if it is independent of theta. If it is dependent on theta, then we will be having both the constants intact, and in terms of the so with the formulation we have just done now, that will be giving you the complete solution. Okay. So, we have, so what we have done, let me summarize. We have seen the problem how the problem of cylindrical polar coordinate can be solved in 2-dimensional case and can be solved in 3-dimensional case. So, that gives us a fair idea. The difference between the two cases, in case of say 2-dimensional case, the boundary conditions on theta will be given by the provided by the periodic boundary conditions. So, these are the physical boundary conditions, they are dictated by the physics of the problem. Next, we will look into the spherical polar coordinate system, and these examples in chemical engineering are many. Spherical polar coordinate system. Whenever we are talking about the heat transfer characteristic in a sphere or in a solid sphere or in a hollow sphere, these equations will be come in place. Now, let us look into the Laplacian operator in spherical coordinate. Grad square is nothing but 1 over r square del r square del r plus 1 over r square sin theta del theta sin theta del theta plus 1 over r square sin square theta del square del phi square. So, this is the grad square, the operator in spherical polar coordinate system. So, r varies from 0 to capital R, theta varies from 0 to pi, and phi varies from minus pi to plus pi. Now, we take up one example first. The first example is solution of grad square u is equal to 0 for r lying between 0 to 1, maybe it is in non-dimensional case, and we have a phi symmetry. If we have a phi symmetry, that means phi varying parts will be equal to 0. So, we will be having only 2 dimension in r and theta, and we put the boundary condition that u at r is equal to 1 should be is equal to in general some function of theta. So, this function of theta may be constant, may be 0, or it may be it may be some, in general it may be some function of theta at r is equal to 1. Now, since we have the non-homogeneity at f of theta, it is independent of phi. So, therefore, u is independent of phi, and we have also the phi symmetry. So, we write down the 2-dimensional problem as 1 over r square del r, r square del u del r plus 1 over r square sin theta del theta sin theta del u del theta is equal to 0. Okay. Now, since this problem is linear, the operator is linear, the boundary conditions etcetera are linear. So, therefore, we break down this problem into two parts, that is one time dependent part and one is the space r dependent part, another is the theta dependent part. So, we assume the two sub problems that is the entirely a function of r and entirely function of theta, they can be multiplied and the product will be given by the will be constituting the solution. So, we separate the variable as we have done earlier, 1 over r d dr of r square dr is equal to 1 minus 1 over t sin theta d theta sin theta dt d theta, and the left hand side is entirely a function of r and the right hand side is entirely a function of theta. So, they will be equal to some constant lambda. Now, the boundary conditions, if you see the boundary conditions in R is non-homogeneous. So, we cannot formulate an eigenvalue problem in the r direction. That has to be made very clear. So, no possibility of formulation of eigenvalue problem in r direction, because the boundary condition is not homogeneous on that boundary. So, let us look into the theta varying part. D theta of sin theta dt d theta plus lambda sin theta t should be is equal to 0. Now, let us fix up the boundary conditions on theta on theta direction, and we know that boundary conditions on theta directions, we do not know the exactly what boundaries are present. So, therefore, we put the conditions so that they becomes physical. So, we use the physics of the problem, and we impose the physical boundary conditions. So, the solution does not become singular. If the solution becomes singular, then the solution does not exist at those points. So, based on that, we fix up the physical boundary conditions on theta. So, if we write it down, t at theta is equal to 0, this is bounded. T at theta is equal to pi, this is bounded. Dt d theta at theta is equal to 0, it is bounded. Dt d theta at theta is equal to pi, again it is bounded. And from where these boundary conditions are coming? These boundary conditions are coming such these are the points of singularity. Since the solution exists at those points, so therefore, we will be having a finite value at those points, and these becomes the singular points, and we impose that the solution becomes bounded at those points. Therefore, these are the perfect examples of physical boundary conditions that we have talked earlier. Now, let us solve this theta varying part. So, theta varies from 0 to pi, and we substitute t is equal to cosine theta. So, if we do that, the form of the theta varying part becomes dt d dt of 1 minus t square dp dt plus lambda p t will be equal to 0 for t varying from minus 1 to plus 1. If you remember, this is nothing but the Legendre equation, and Legendre polynomial is the solution of this Legendre function and Legendre polynomial. So, solution is p of t is nothing but c n p n t plus c 2 c 1 p n t plus c 2 q n t. Now, p n is nothing but the Legendre polynomial, and this is nothing but Legendre function. And this p is nothing but the the r varying part. We identify this is nothing but the r varying part. This is basically equal to r. I just wrote it in the form of p. So, it does not matter. So, if you look into this problem, we have seen earlier the eigenvalues lambda n are the eigenvalues to this problem. The eigenvalues, we have discussed this for properties of the Legendre polynomial Legendre function earlier. The eigenvalues are n into n plus 1, and where the index n runs from 0, 1 to so this p r, this is there is one mistake, this p is not r varying part, it is a theta varying part. Sorry, we are solving the theta. So, we make it at r theta varying part, because we are solving the eigenvalue problem in the theta direction, not in r direction, because r direction itself is boundary condition is homogeneous. So, we cannot formulate the eigenvalue problem in the r direction. So, this is the solution, this is the governing equation of theta varying part after substituting t is equal to cosine theta, which will be in the form of the Legendre equation, that will be having solution in terms of Legendre polynomial and Legendre function. Therefore, we can solve the theta varying part completely, and P of, and if you look into the property of eigen the Legendre function, the property is q n is unbounded, the Legendre function is unbounded at t is equal to plus minus 1. Therefore, the associated constant with this must be equal to 0. So, we will be having the P of t is nothing but C n P n t are the eigen functions. In terms of t, the theta varying part, t of theta should be is equal to C n P n cosine theta. So, this is the theta varying part, and that is the eigen functions in the theta varying part. And eigenvalues are n into n plus 1, where the index n runs from 1 to infinity. Now, let us go back to the r direction and see how we can solve that part in the r direction. We cannot formulate the eigenvalue problem in the r direction, simply because we have the non-homogeneous boundary condition there. So, we write it at r subscript n corresponding to nth eigenvalue. So, d dr of r square dr n dr is equal to minus lambda n is equal to 0. So, if you just open up this differentiation, this becomes r square dr n d square r n dr square plus 2 of r dr n dr minus n into n plus 1 r n is equal to 0. So, lambda n is nothing but n into n plus 1. So, therefore, this is the equation. Now, if you remember, if you recognize this equation is nothing but Euler's equation. When we were discussing about the special ordinary differential equations, we discussed about the Bessel equation, we discussed about the Legendre equation, we discussed about the Euler's equation. So, this is an application where Euler's equation will be coming into play, and we have to look for the solution of this equation. Now, if the solution of this equation, the solution of this equation will be in the form of r to the power alpha. So, it will be getting a quadratic, as we have seen earlier. This alpha becomes either n or minus n minus 1. So, these are the two roots of the quadratic. So, solution becomes r n of r is C 1 n r to the power n plus C 2 n r to the power minus n plus 1. Now, if you remember that we have the boundary condition that at r is equal to 0, this r n was finite or bounded. In order to satisfy this boundary condition, the associated constant has to be equal to 0. Therefore, r n is equal to r is nothing but C 1 n r to the power n. So, therefore, u r theta u n r theta becomes combination of C 1 n and t theta. So, it will be some constant multiplied, let us say C n multiplied by r to the power n p n cosine theta. Now, this is the corresponding nth solution corresponding to nth eigenvalue. The complete solution can be obtained if you sum up all the contributions. So, u as a function of r and theta becomes summation n is equal to 0 to infinity C 1 n r to the power n, maybe C n r to the power n p n cosine theta. So, that is the solution. Now, we have one constant, integration constant C n has to be evaluated. and if you remember, we have one condition that is still remains unutilized. What is that condition? That condition is at r is equal to 1, your u r theta is non-homogeneous. So, at r is equal to 1, u is equal to f of theta. So, therefore, we utilize this boundary condition and evaluate the constant C n. So, f of theta is nothing but n is equal to 0 to infinity. When we are evaluating r, so this becomes 1. So, this will be nothing but C n p n cosine theta, and we can prove that p n cosine theta is orthogonal function with respect to weight function sin theta. So, therefore, if you remember, in the Cartesian coordinate, the sine function and cosine functions are orthogonal function with respect to weight function 1. In cylindrical coordinate, the Bessel functions are orthogonal function with respect to weight function r. In the spherical polar coordinate, the the eigen functions are orthogonal to each other with respect to weight function sin n theta. So, therefore, we write down the complete solution. We multiplied both sides by p m cosine theta d theta and integrate over the theta, that is 0 to pi. So, you will be getting the all the terms will vanish except the except m is equal to n. It will be 0 to pi f of theta p n cosine theta sin theta d theta, because it is in a weight function. So, 0 to pi p n square cosine theta sin theta d theta. So, that gives the estimation of the integration constant C n. So, once we get the estimation of integration constant C n, we can put it back here and we will be getting the complete solution in r and theta. Okay. So, next we look into one more example. This example deals about the spherical coordinate, but it is not 2 dimensional, it is a 3 dimensional problem. 3 dimensional problem in spherical coordinate. Okay. So, no phi symmetry in this case. So, the condition, the boundary condition at r is equal to 1, you have u is equal to f theta and phi in general. So, it may be a function of theta alone, it may be a function of phi alone, it may be a constant, it may be function of theta and phi both. In the earlier case, if you remember, we had the condition that r is equal to 1, u is equal to f of theta. So, we constitute the solution as a function of r theta phi by multiplying 3 functions which are function of r alone, theta alone and phi alone. We am just writing them, r as a function of r, theta as a function of theta and capital phi as a function of phi. So, if you substitute in the governing equation of Laplacian in spherical polar coordinate system and then separate the variables, you will be getting this. I am not solving this for you, please do it by yourself. We have done this type of things lots of times earlier. So, differentiation is with respect to the variable. So, plus sin theta theta prime of that divided by theta sin theta sin square theta is equal to minus phi double prime divided by phi. Here the prime is with respect to small r, here the prime is with respect to small theta, here the prime is double prime is with respect differentiation with respect to small phi. Now, we put it as a constant. So, the left hand side is a function of r and theta only, right hand side is a function of phi. So, we put it as a constant. So, we have 4 boundary conditions on phi. These are the periodic conditions. periodic boundary conditions. So, 4 boundary condition means they will be equal periodic boundary conditions. So, boundary condition phi we define as phi at pi is equal to phi at minus pi d phi. So, this is capital phi d phi at pi is equal to d phi at minus pi. So, these are the periodic boundary condition, these are the physical boundary condition. We use the periodic boundary conditions here. So, we can find out the eigen values and eigen functions in the phi direction. So, if you do that, the eigen values becomes mu square is equal to m square, that we have already seen, and m is equal to from 0, 1, 2, 3 up to infinity. We have already seen this thing in earlier case and therefore, phi is nothing but a m sin m phi plus b m cosine m phi, where the index m runs from 0, 1, 2 up to infinity. In case of 3-dimensional cylindrical polar coordinate, we have a situation like this with the periodic boundary conditions, and we have seen there as well that the eigen functions are constituted by the sine function and cosine function. So, in this case also we will be getting the eigen function as usual, which will be constituted by the linear combination of sine function and cosine function, and the index m runs from 0, 1 to infinity instead of 1 to infinity. So, that solves the phi varying part completely. Then we will be looking into the theta varying part and r varying part, and we will be constructing the solution completely in the next class. So, I stop it here. In the next class, I will be completing this problem, and then we will look into the solution of partial differential equations, but those are non-homogeneous using Green's function method. Thank you very much.